So we just saw a video of the same curve being traced out when we use different parameterizations. And this is a good time to once again remind you that whenever we have a parameterization of a curve, we have two ways of, or two pieces of information that we can get out of that. We, one, know what the actual curve is, but by introducing a parameter, it gives us a measure of how we actually trace that curve out. So the thing is that we want to make sure that we are working with a uniform type of parameter when we're talking about curves. And one of the things that we really care about in calculus is making sure that we can move small distances along curves. And we define things like derivatives, and we define things like curvature of a curve. Many different applications require that we know that we're moving a small distance along the curve. And so I want to take this time to say that there are sort of what the actual difference is between these parameters. So we have this general given a curve described by r of t. We can think of this t as a time parameter, if you will. In other words, this tells me a way to trace out the curve, and this r of t, which I'll write out as what it always is. The first component will be x, the second will be y, the third will be z. This will give me, for a given value of t, this will tell me, so the r of t here will tell me the location x, y, z at time t. So the thing is, if this curve is, say, being traced out, if it represents the motion of, say, my grandmother walking along a path, or say a photon zipping along the path, time is not necessarily going to measure anywhere near the same thing. So in order to have a uniform parameter, it makes sense to say, well, let's not think about how we're tracing this out in time. Let's think about how far are we going along the curve. So we want to introduce a new parameter, which we'll call the arc length parameter. That measures how far we've gone along the curve from some starting time t is equal to a. Normally we let that be 0, but we won't do that yet, to a future time. And s is going to be that distance. So now this new parameterization of the same curve, r of s, this will tell me x is a function of s, y is a function of s, and z is a function of s. S measures how far we've gone. So this gives me the x, y, z on the curve if we travel s units from the starting location. And so this is nice because whether my grandmother has moved 1 unit along the curve or a photon's moved 1 unit along the curve, we've moved 1 unit along the curve. They're going to be at the same place. So this is a very sort of natural parameter to introduce. And we're going to ask next, well, how does that relate to the original parameter, right? If t measures, if we think of t as time, then the distance that we travel certainly will depend on how long we've traveled. And we're going to talk about that in a second.